This is section 4.7, inverse trigonometric functions. This will be a one-part lesson. Now, before we talk about inverse trig functions, it's very important for us to do a quick review of the unit circle. The unit circle is your best friend in trig. All right, it's your best friend in trig. We talked about the unit circle earlier. We talked about the concepts. The basic concept, of course, is that since the radius is 1, anything over 1 is itself. And the whole beauty of the unit circle is that the magnitude of arc length equals the magnitude of the corresponding angle for each of these pi sectors. So that's the basic principle of the unit circle. And if you want to review the unit circle, you can certainly rewatch that video. I believe it's video 4.2. But the reason that I want to bring it up now, first of all, it has to do with inverse functions. We're going to get to that in a bit. But second, it's a principle that is sometimes forgotten about trig, and that is the following. To really master trig, you have to do some memorizing. Okay, think of it like when you were learning times tables, you had to memorize them. And you know, it's not that you didn't understand the times tables, but for the sake of speed, you have to memorize them. Imagine doing math now and not having your times tables memorized. You know, we take it for granted that 9 times 6 is 54, or that 8 times 4 is 32. You know, we don't even have to think about it. If we sit down and write it out and do it step by step, and you know, do 4 times 8 by adding 4 8 times, you know, we'll get the right answer, but it takes too long. So my main point is that to really master trig, you do have to do some memorizing. You have to do some memorizing. And your memorizing consists of two basic areas, okay? This is one of them, the unit circle. The unit circle is about half of what you need to memorize for trig. The other half is trig identities, which we're going to get to in Chapter 5, being able to know and manipulate trig identities. Both trig identities and the unit circle are fundamental for calculus. So you need to memorize both of them for the sake of this class and for the sake of next year's class. Don't worry about trig identities for now, but for now, definitely make sure that you master the unit circle. You can start out in your mastery of the unit circle by copying down this screen meticulously. Every mark on this screen should be in your notes. And I would recommend not even just putting it in your notes. Make a little 3x5 index card that has everything on this screen exactly as it's written, because it's going to help you. Even the little red angles that I have here, negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 6, even those are important, and put them in a different color for reasons that we're going to see a little bit later in this video. But what you should do is copy this down. And if you can't memorize it right away, know that your goal is to have it memorized. Okay, before we get into specifics, let me just give you a little trick about memorizing. Let's say that you, let's say you sit down at a test, or you're somewhere doing problems. You don't have your unit circle with you. You want to construct one. Well, the endpoints are very easy. You know, you've got 1, 0, that's here. You've got 0, 1, that's up there. You've got negative 1, 0, and you have 0, negative 1. So you start with those 4. And then constructing these points that are on the sectors with these common angles, you know, pi over 6, 30 degrees, this is one sector here. And as we talked about in the video for 4.2, the great beauty of the unit circle is that for any point that is on the circle itself, the circle itself, the x-coordinate corresponds to the cosine of the angle, and the y-coordinate corresponds to the sine of the angle. And the tangent, of course, is simply the sine over the cosine, or the y-coordinate over the x-coordinate gives you the tangent for that angle. All right, so if you are trying to construct a unit circle from memory, notice the pattern. Okay, from 0, 1, looking at the x-coordinates, going all the way down the circle to 1, 0. Look at what happens to the x-coordinates. You have root 1 over 2, then you have root 2 over 2, then you have root 3 over 2. It's 1, 2, 3, as easy as 1, 2, 3. So with the cosines, going from up to down, it's 1, 2, 3. Root 1, or 1 half, root 2 over 2, and root 3 over 2. With the sines going from the sine of 0, or the y-coordinate of 0, all the way up to the sine of 1, or the y-coordinate of 1, it's also as easy as 1, 2, 3. Root 1 over 2, root 2 over 2, root 3 over 2, root 3 over 2, and it goes in that order, 1, 2, 3. So that's one way, that's a way that I like to remember the unit circle, so that, if I just am anywhere and I don't happen to have my unit circle with me and I need it, I can just construct it from memory. And I like to think of it as being as easy as 1, 2, 3. Now, that of course is not the only mnemonic device. You can use others. There are many different ways to memorize things. I'm just giving you one. But the basic point I'm trying to make is that you do have to memorize the unit circle. All right, I'll repeat that till I'm blue in the face. Memorize, 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 memorize the unit circle. Okay, so we have our common angles here, pi over 6, which is 30, pi over 4, which is 45, pi over 3, which is 60, and then pi over 2 is 90, and then all these multiples of those angles. This makes up our unit circle. The reason I have these angles in red here, negative pi over 2, is the same as 3 pi over 2. It's just that you're proceeding clockwise from the positive x-axis rather than counterclockwise. Negative pi over 3, same thing. Negative pi over 4, equivalent of 7 pi over 4. Negative pi over 6, equivalent of 11 pi over 6. And note also that you have your x and y coordinates of all these different points that are on the unit circle. For example, this, where my mouse arrow is pointing now, notice where my mouse arrow is pointing now, I'm just drawing it around a point that is actually on the unit circle. And that point has an x-coordinate of root 3 over 2 and a y-coordinate of 1/2, which means, because this is the unit circle, that for that point, which happens to be the arc, or to trace out the arc for the common angle pi over 6, 30 degrees, at that point, my cosine is root 3 over 2, and my sine is 1/2. And that is the cosine and sine for the angle pi over 6. Okay, so once you have this completely copied down, both in your notes and on a note card, because you're going to need to memorize it, and then until you memorize it, you're going to need to refer to it. Once you have that done, then you can proceed to the next screen. The inverse sine function. Recall that for a function to have an inverse, it must be a one-to-one function and pass the horizontal line test. Let's look at the sine function, y equals sine x. Well, we can see from that horizontal blue line that it does not pass the horizontal line test. Therefore, its domain must be restricted to find its inverse. Do you remember when we were doing inverse functions in Chapter 1, and we saw how the function y equals x squared, just that simple parabola y equals x squared, does not have an inverse because it doesn't pass the horizontal line test. However, when you restrict the domain of y equals x squared to 0 to infinity, that is, from 0 to positive infinity, when you restrict the domain of y equals x squared in that way, then it does pass the horizontal line test, then it is one-to-one, and then it does have an inverse, and that inverse is y equals square root x. Okay, so just as we did for y equals x squared, restrict its domain in order to make it invertible, we're going to do the same exact thing with the sine, cosine, and tangent functions. So, for the sine function, we restrict the domain to this red portion. From negative pi over 2 to pi over 2, we restrict the domain, and on that interval, the sine x function does have an inverse. Because it's one-to-one and passes the horizontal line test. The inverse sine function is defined by y equals arc sine x. Arc sine x only if sine y equals x. So the best way to think of y is the angle whose sine is x. And some examples of that, and you can refer to your unit circle for this. Look at your unit circle, which you diligently copied down from the first screen that we had of this lesson. And you'll see that the inverse sine, or arc sine, 1/2 is pi over 6. because pi over 6 is the angle whose sine is 1/2. In terms of the unit circle, pi over 6 is the angle whose corresponding point on the unit circle has a y-coordinate of 1/2. And you can clearly see that on your unit circle. Look for the pi over 6 pi piece. Look for the point on the unit circle that corresponds to that pi over 6 pi piece. Look at the x and y coordinates of that point, and you'll see that the y-coordinate is 1/2. Inverse sine root 3 over 2 equals pi over 3 because sine of pi over 3 equals root 3 over 2. By the way, that's this little -1 exponent. It's not an exponent. It's just a symbol for inverse, just as we saw in chapter 1 when we were doing inverse functions. The -1 that looks like an exponent is just a symbol for inverse. So the inverse sine function can be written in two ways, and this applies also to the inverse cosine and inverse tangent. You can either write it as arc sine or as inverse sine, or sine minus 1 with a -1. That's read, the way that is read is inverse sine, inverse sine. And of course, for example B, you can confirm this by looking at your unit circle. Remember that the unit circle is your best friend for trig, and it's very useful. You can use it for a lot of things. You can see that the y-coordinate for the point that is on the unit circle and borders that pi over 3 sector or pi piece does have a y-coordinate of root 3 over 2. That is the sine of pi over 3. Therefore, the inverse sine of root 3 over 2 is pi over 3 because it's the angle whose sine is root 3 over 2. Graph of the inverse sine function. You definitely want to refer to this often. So you're going to write it down. You're going to diligently copy down this screen too. Of course, it's not like you have to memorize it as much as you do the unit circle. But it's important to realize where this graph comes from. Okay, so we have our arc sine function. Now on the left of the screen, I have just the arc sine or inverse sine function by itself, and then on the right portion of the screen, I have the arc sine function and the sine function on the same set of axes to show the relationship between the two. First of all, let's go over here to the right. And let's look at the parent sine function. Notice that the sine function here, the portion of it that we're dealing with, is in light gray, and the inverse sine function is in dark gray. And now let's just look at the light gray curve. We have sine x, and that's our light gray curve. All right. Notice how the domain has been restricted. It's just from negative pi over 2 to pi over 2. Notice here that on this x-axis we have the grid marks in -1, and each tick mark is worth a quarter unit. So following the mouse arrow now, if you look at it, I have this would be negative 0.25, and then negative 0.5, and then negative 0.75, and then -1, etc. Well, negative pi over 2 is about 1.5. It's a little more than 1.5, and as you can see, that's what we have here. We have a little more than 1.5, negative 1.5. And if we go over here to the right side of the sine x domain, you see that the positive endpoint of the sine x domain is a little more than 1.5, which is the same as being pi over 2. Okay, so we've got our domain. We also have our range for this portion of the sine function that goes from -1 to 1. And so I have that written in gray at the bottom of this screen. So the bottom right portion of this screen, we see it says domain of sine x is negative pi over 2 to pi over 2. That's the restricted domain. And the range of that restricted function is -1 to 1, which happens to coincide with the range of the regular function. Okay, now look at now the darker gray. This is inverse sine x. Notice how the graphs relate to each other because they are symmetric about the line y equals x. They have symmetry about the line y equals x. And that's because the x's and y's are swapped, which we learned in chapter 1. And also, look how the domain of the sine, the restricted sine function, is negative pi over 2 to pi over 2, which is the range of the inverse sine function, negative pi over 2 to pi over 2. Notice also that the range of the sine function, the restricted sine function, is negative 1 to 1, and that, of course, is the domain of the inverse, negative 1 to 1. Okay, because the domains and ranges are swapped with inverse functions. Okay, so make sure that you have this screen copied down and observed. You will sometimes need to refer to the graph of the inverse sine, mainly because sometimes it's hard to keep track of where we have restricted the domain. And we'll see an example of why this is important a little bit later today. Inverse cosine function. As you can see, the inverse cosine function doesn't pass this horizontal line test. And therefore, just as we saw for sine, the domain of the cosine x function must be restricted to find its inverse. And we're going to restrict it to this portion, from 0 to pi. The portion from 0 to pi is the restricted interval, and the cosine function does have an inverse on this interval. The inverse cosine function is defined by y equals arc cos x only if cosine y equals x. And the angle whose cosine is x is the best way to think of y in this case because it makes more sense. For example, let's look at arc cos 1/2 equals pi over 3. That just means the angle whose cosine is 1/2 is pi over 3, or pi over 3 is the angle whose cosine is 1/2. Refer again to your unit circle, and sure enough, you will see that for the x-coordinate of 1/2, the x-coordinate of 1/2, that angle is pi over 3. Okay, so find the point right now. Find the point on the unit circle. It's a point that's in the first quadrant, and look for a point that has an x-coordinate of 1/2. That x-coordinate, of course, is a cosine because we're talking about the unit circle. And sure enough, it is for the angle pi over 3, or 60 degrees. Inverse cosine negative root 3 over 2 equals equals 5 pi over 6. The negative 1 sign, of course, is just a symbol for the inverse cosine. And refer to your unit circle, and you will see that over there in the second quadrant, the x-coordinate of negative root 3 over 2 corresponds to the angle 5 pi over 6. Notice also, and this is where the domains and ranges come in, the range of the inverse sine function is from negative pi over 2 to pi over 2. But the range of the inverse cosine function is from 0 to pi. And that's why 5 pi over 6 is a possible value when we're evaluating an inverse cosine. 5 pi over 6, it's in the second quadrant, but it's still between 0 and pi. Let's look at the graph of the inverse cosine function. Now we can see, as I just said in the last screen, that the domain of the restricted cosine function, if you look at the right half of this screen, the domain of the restricted cosine function is 0 to pi. 0 to pi. The cosine function, is invertible on that interval. And notice that the domain of the cosine function is equal to the range of the inverse cosine function, and the range of the cosine function is equal to the domain of the inverse cosine function. Look also at the graphs, see how they relate to each other. When you graph them on the same set of axes, they are symmetric about the line y equals x. They have that diagonal symmetry because the x's and y's have been swapped. Notice also the limitation of my domain here. If we look at the lighter gray curve, the cosine x curve, the domain is from 0 to pi, 3.14159. From 0 to pi, we see that here in the x interval, and the y interval, or the range, is from negative 1 to 1. That, of course, is swapped with the inverse cosine, who has a domain of negative 1 to 1, but a range of 0 to pi. Inverse tangent function. Again, it does not pass the horizontal line test, but we can restrict its domain to find its inverse. And we restrict it just to that first period, which goes from negative pi over 2 to pi over 2, negative pi over 2 to pi over 2. And on that interval then, the tangent x function is invertible. It does have an inverse. The inverse tangent function is defined by y equals arc tan x, only if tan y equals x. The angle whose tangent is x is how we understand y. By the way, quick little side note, just in case you're wondering why it's called arc sine, arc cosine, or arc tan, it's straight from the unit circle. Remember that the whole beauty of the unit circle is that for each of those pi sectors, the arc length has the same magnitude as the angle. Okay, and therefore, since calculators actually use their built-in unit circles to calculate inverse sines, inverse cosines, and inverse tangents, it's why we call it an arc sine or an arc cos or an arc tan, because it comes straight from the unit circle and from the beautiful fact that on a unit circle, magnitude of arc length equals magnitude of angle. Examples: arc tan root 3 over 3 equals pi over 6. Pi over 6 is the angle whose tangent is root 3 over 3. Now, the arctan is a little bit trickier. You see, with arc sine and arc cosine, all you have to do is look at the x-coordinate or the y-coordinate on your unit circle. Well, with tangents, it's a little bit trickier because it's not enough just to look at x or y. You have to look at y over x. So you need both. You look at y over x, that ratio. And if you refer to your unit circle right now, and you look at that pi sector, pi over 6, okay, that little pi piece there, if you look at pi over 6, you'll see that its corresponding point has an x-coordinate and a y-coordinate. Well, if you divide and you go y over x, the y-coordinate divided by the x-coordinate, you'll quickly see that it simplifies to root 3 over 3. It simplifies, of course, to 1 over root 3, but 1 over root 3 is the same as root 3 over 3. The same exact thing. Root 3 over 3 is the same as 1 over root 3. And that is equivalent to y over x on the unit circle. Y over x on the unit circle for pi over 6 is root 3 over 3. How about inverse tangent 1? Well, if you look at unit circle here, you'll see that you do have a ratio of 1 where the y-coordinate equals the x-coordinate for a certain angle there in the first quadrant. It's 45 degrees, or pi over 4, because you have root 2 over 2 for your x-coordinate, you have root 2 over 2 for your y-coordinate, and root 2 over 2 divided by root 2 over 2 is 1, and that corresponds to the sector for pi over 4 on the unit circle. Therefore, arctangent 1 equals pi over 4. Here's the graph of the inverse tangent function. So on the left we see y equals arctan x. On the right we have both the tangent function and the inverse tangent function on the same set of axes. Notice again, as we did for sine and cosine, that these two graphs are symmetric about the line y equals x. Also notice, let's look first at the light gray curve, which is the tan x function. The dotted lines in gray are asymptotes for that, and of course the asymptotes go from negative pi over 2 to pi over 2 because those are the endpoints of our restricted domain. Negative pi over 2 to pi over 2, and you can verify that just looking at this. You know that pi is about 3.14159 divided by 2, you got about 1.5, and that's why we have about 1.5 here, because it's negative pi over 2. And same goes for here on the right side, pi over 2. So that would be the domain. The range is negative infinity to infinity. You can see that the graph extends infinitely below the x-axis and infinitely above the x-axis. As we did in the previous two inverse trig functions, notice that the domain of the tangent function is the same as the range as the inverse tangent. The range of the inverse tangent. The range of the inverse tangent is negative pi over 2 to pi over 2, but not including those endpoints, of course, because those endpoints are asymptotes. The range of the parent tangent function, this restricted function that we are inverting, its range is negative infinity to positive infinity, and that's the domain of inverse tangent, or arctan. So the domains and ranges have been swapped because one function is the inverse of the other. We're going to use the unit circle for the examples on this screen. So using only the unit circle, not your calculator, find the exact value of each expression in radians. Here's the first one. Do inverse cosine negative root 2 over 2. All right, so remember you're looking for an x-coordinate. You're using only the unit circle. And pause the video and then resume when you have an answer. 3 pi over 4, that's the right answer, 3 pi over 4. Now, you may have noticed that there is another multiple of pi over 4 that also has an x-coordinate of negative root 2 over 2, right? And you might wonder, well, how do you know which one to choose? Here's how you know which one to choose. You have to remember the range of the inverse cosine. The range of the inverse cosine is 0 to pi. Therefore, any angle that is greater than pi is not a valid answer. Okay, so if you find an angle in the fourth quadrant that does have an x-coordinate on the unit circle, an x-coordinate of negative root 2 over 2, that cannot be the answer because it's out of the range of the inverse cosine function. And the only angle that is it's in the interval 0 to pi, so the only angle within the range of the inverse cosine function, which has a cosine of negative root 2 over 2, is the angle 3 pi over 4. 3 pi over 4 is the angle whose cosine is negative root 2 over 2. Okay, so this is definitely where you want to make sure that you either know by heart or have always with you written down somewhere the range of the inverse cosine, the range of the inverse sine, and the range of the inverse tangent, because that will determine how to make a choice when there's any ambiguity. Arc sine negative root 3 over 2. Pause the video, do that on your own using only the unit circle, and then resume when you have an answer. Negative pi over 3. Negative pi over 3. Okay, that's the main reason for choosing this, negative pi over 3, of course, is that the range of the arc sine function is from negative pi over 2 to pi over 2. Okay, and the only angle within that range whose sine is negative root 3 over 2 is negative pi over 3. This again is the importance of writing those little red numbers on the unit circle that was on the first screen of this video, because those little red numbers help you to easily convert to a negative angle instead of a positive obtuse angle, right? You have this negative acute angle, negative pi over 3, negative pi over 3, which corresponds, of course, to 5 pi over 3. But since 5 pi over 3 is not in the range of the inverse sine function, we must choose negative pi over 3. Arctan root 3. Pause the video, do this on your own using only the unit circle, then resume. Pi over 3. Pi over 3 is an angle whose tangent is root 3. And you get that by dividing y by x. Dividing y by x. So you look at your unit circle, you look at your x and y coordinates, and where there is a ratio of y over x that is root 3, or if you like, root 3 over 1, that only occurs at pi over 3, because you have root 3 over 2 divided by 1/2, and that is the same as root 3. Inverse tangent negative 1. Pause the video, do that on your own, then resume when you have an answer. Negative pi over 4. Negative pi over 4. Again, it's very important to remember the range of the inverse tangent. Since the range of the inverse tangent is from negative pi over 2 to pi over 2, we must express the angle whose sine is negative 1 in those terms. That's why we choose negative pi over 4. Of course, that is the same as 7 pi over 4, but since 7 pi over 4 is outside of the range of the inverse tangent, we must choose negative pi over 4 as the equivalent. Now we're going to use a graphing calculator, and you may have done this before. Maybe you did it last year when you were introduced to trig. But in any case, the main thing here is just be familiar with your calculator and know where the inverse sine, inverse cosine functions are. Now, I know that there are many different calculators out there, but in the TI-83 Plus family, which most of us are using, you can very easily see the inverse sine, the inverse cosine, and inverse tangent functions right above the sin, cos, and tan buttons on your calculator. And you'll notice that the sine minus 1 or inverse sine, and cos minus 1 or inverse cosine, tan minus 1 or inverse tangent, those are all written above the sin, cos, and tan buttons. And you can use the second button to choose those inverse functions. Okay, now notice how the directions here say approximate the value of each expression in degrees. So if you haven't done so already, you want to make sure that your calculator is in degree mode. And for that, you go to the mode button, and once you press the mode button, you'll see you have a bunch of options. And you'll see that you've got, on the third or fourth line down, you have radian or degree. Choose degree, and that'll put your calculator in degree mode. Okay, so first exercise, inverse cosine of negative 0.75. Pause the video, do that, and then resume when you have an answer. 138.59 degrees. All right, and notice that 138.59 degrees is in the range of the inverse cosine, which is from 0 to pi, same as 0 to 180. And so 138.59 is definitely in that range for the arc cosine, the inverse cosine function. Arc sine 0.19. Pause the video, do that, and then resume. 10.95 degrees is the correct answer. Arctan negative 1.32. Pause the video, do that, and then resume. Negative 52.85 degrees. Notice that that is also in the range of the arctan function that goes from negative pi over 2, that is negative 90 degrees, to pi over 2, that is 90 degrees. So negative 52.85 is definitely in that range. Inverse sine 2.5. Pause the video, do that, and then resume. Error. Why is that not possible? Because, of course, 2.5 is not in the domain of the inverse sine function. Now, some of you may have recognized that right away, but if you didn't, that's okay, because you haven't really had much time to get familiar with inverse functions yet. But when you're dealing with inverse functions, you need to keep in mind the domains and ranges. And since the domain of the inverse sine, you can review that from a previous screen. Since the domain of the inverse sine is from negative 1 to 1, then 2.5 is impossible. There is no inverse sine of 2.5. Just in case any of you are curious, that's how the calculator does the inverse sine functions. It just uses a unit circle. But of course, a calculator's unit circle has every possible point, or can trace every possible point that's on the circle. It doesn't only trace the common angles. That's on our, our paper unit circle that we need to memorize. But the calculator has a built-in unit circle that, like, for example, if you want to find the inverse sine, or let's look at example A, inverse cosine negative 0.75. The calculator literally just looks for the point that has an x-coordinate of negative 0.75 on the unit circle, and then it finds the equivalent angle. Composition of functions. We saw this in chapter 1 when we were doing inverses. So f of f minus 1x equals x, and f minus 1 fx equals x. F minus 1 is one way to read it, but really it's better to read it as just f inverse, because the negative 1, as said so many times before, is not an exponent. It's just a symbol. So f inverse x, or f of f inverse x equals x, and f inverse of f of x equals x. An inverse function simply undoes the original function. And the original function undoes the inverse. They undo each other. That's why they're called inverses. It's the nature of inverse functions. Inverse properties. This is the main intrinsic property of inverses, is that they undo each other. So, of course, sine of arc sine x is just x, and arc sine of sine y is just y. And this first line here, if -1 is less than or equal to x is less than or equal to 1, and negative pi over 2 is less than or equal to y is less than or equal to pi over 2. All that is just restricting domains. You don't need to worry about that part. Because the main thing here is that the sine function undoes the arcsine function and vice versa. Same is true, of course, of the cosine function. Is that the cosine undoes the arc cosine and vice versa. And of course, it also applies to tan and arctan in the same exact way. Example, tan of arctan 4 is just 4. Okay, so that's simple. It's really just a consequence of the definition of inverses. That's all it is. Simplifying expressions. Find the exact value of tan arc cos 2/3. All right, so you don't need a graphing calculator for this. You don't need any buttons on your calculator. In fact, you can do this without a calculator at all. And you should do it without a calculator at all. But what you need to do is figure this out. Now, this is a good exercise for you because especially in the next section, we're not really doing new trig concepts, we're just applying them all. The challenge of trig is not just learning the concepts, but applying them in creative ways. Sometimes that's really what makes the word problems hard, and we're going to be doing pretty much all word problems the next section. All right, so try to figure this out, and then when you have an answer, resume the video to see the solution. Okay, here's what you do. You let u equals arc cos 2/3. Now, you don't have to call it u. You could call it x or y or q or whatever. But the point is, without knowing what the angle u equals, you do know that it has a cosine of 2/3. And since you know that cosine is adjacent over hypotenuse, you can draw your own right triangle, and you can label that adjacent side with 2, label the hypotenuse with 3, and then you can use the Pythagorean theorem to go from there, because you know that the shorter leg is just going to be square root of 3 squared minus 2 squared. Okay, that's just a consequence of the fact that shorter leg squared plus longer leg squared equals hypotenuse squared. And so the answer then, since you were asked to find the tangent of u, or whatever you want to call it, and since tangent is opposite over adjacent, then the answer is root 5 over 2. Root 5 over 2. Classwork, page 350, please write these numbers down, and see you in class.